In the past 60 years or so, human activity has contributed to the destruction of the ozone layer. The problem is more serious at Antarctica. From the figure, we can see that the ozone hole at Antarctica is becoming remarkable in recent years. However, the ozone hole at Antarctica is not always happening. From this figure, we can figure out that the concentration of ozone reaches the lowest in September and October at Antarctica. The figures from NASA also show that the concentration of ozone at Antarctica is not low compared to the ozone concentration in other parts of the Earth in autumn and winter. The similar result is also shown from the data in summer. However, the data in September shows that the ozone concentration at Antarctica is significantly lower than the ozone concentration at other latitudes. Thus, we can conclude from the data that the ozone hole always occurs in the Antarctica in September and October. But why is that? We try to address the question by this short video. Firstly, the ozone stratospheric clouds (PSC) could form in wintertime at Antarctica because of its extremely cold temperature. The PSC could form when temperature is below minus 77 degrees Celsius. From the figure, we can find out that the temperature of the lower stratosphere at Antarctica is always below minus 77 degrees Celsius during the winter, which is mainly because of no sunlight and little vortex. Thus, PSC could form at Antarctica during the wintertime. Then, heterogeneous reactions on PSC particle surfaces convert chlorine reservoir species to chlorine. We also need to notice that the composition of PSC is nitric acid trihydrate particles. Large nitric acid trihydrate particles can sediment out, removing nitric acid from stratosphere, which is called denitrification. Then the Antarctica spring comes with the warmer temperature and the returning of sunlight. The remaining PSA evaporate because of the warmer weather. And chlorine that had accumulated from PSA heterogeneous chemistry can now photolyze to form chlorine radical because of the returning sunlight. The chlorine radical, together with CaO, could accelerate destroying ozone catalytically. This is a loss cycle indicating the loss of ozone. Furthermore, please recall the denitrification process during the winter time. This process could lower the concentration of NOx, since the reservoir species nitric acid could not turn back to NOx because of the sedimentation. This means that less CaO could be removed, which would further accelerate the loss of ozone in September and October at Antarctica. Thus, we can conclude that great ozone loss at Antarctica in September and October could cause the ozone hole at this time. After October, Antarctica vortex breaks up, allowing mid-latitude air with more ozone and NOx to mix in. The increasing concentration of NOx could send some of the chlorine to reservoir species. Thus, it decreases the chlorine radical species and further decreases chloride catalyzed ozone loss. As a result, ozone hole could recover after October in Antarctica. From the analysis, we can find out that the ozone hole at Antarctica starts with chlorine species. From the left figure, we can find out that the concentration of the equivalent effective stratospheric chlorine begins to decrease after 1997 because of Montreal Protocol. And the ozone concentration at stratosphere from 60 degrees north to 6 degrees south begins to recover at about the same period. So what about ozone hole change after the Montreal Protocol? From the figure on the right side, we can figure out that the average concentration of ozone from October the 15th to 31st stopped decreasing at about 1997, indicating that Montreal Protocol effectively prevents the problem of Antarctica ozone hole in springtime from getting worse. Of course, we should know that a long period is needed before ozone concentration at Antarctica coming back to its original level during the springtime.